Hello there all. Today what we're going to talk about is more practice with exponential growth and decay. So I want to review real fast before we get before we get into things, some of the formulas, because we're going to be looking at a lot of word problems today. So exponential equations in context. So first of all, we have the generic standard form of an exponential equation, where A is the starting amount and B is however it is changing. Okay, now, we frequently refer to R, or the ratio, as B when I'm writing equations. So just kind of be flexible if you see that. Okay, so this is the growth formula. You know it is growth because it has R. We do not typically write it as 1 plus R, okay? We normally actually do the arithmetic and write it after we've done the addition. If it is decay or losing value, we write it as 1 minus R. Again, same thing. We typically do this after we've done the arithmetic is when we write it in. Now, other common forms are doubling, hence it's a 2, tripling, meaning it's a 3 on the inside, or halving, so it's a 1/2 inside the parentheses. Note that in all of these cases, that A is the amount that we start with, okay? Whether that's money, whether that's the number of bacteria, what have you. Okay, now there's a couple things we have to pay attention to here, some details. Okay, so if we're looking at percent increase and decrease, we often have to be sure that we know what the percent is of that increase or decrease. All right? And oftentimes, they give us the equation. So when you're looking at the equation, we have to be able to look at that and figure out what that percent is very quickly. All right? So let's just say that we have this generic formula here. So we have y equals 9 times 0.86 to the x. Now, first things first, I have to determine, is that an increase or a decrease? Is it a growth or is it a decay? Well, how I know is because this number is less than 1, it is decay. But then I have to figure out how much. So because it's decay, I know it's 1 minus R, if you refer back to our original formulas there. So as I'm doing this, okay, then I just solve this equation. I subtract 1 from both sides. That leaves me with negative R equals negative 0.14. Divide both sides by negative 1. And I get R is 0.14. And after I move the decimal point 2 places, that is 14%. Okay, so that would be a 14% decrease. Now, if it is growth, frequently we'll say you put so much money in a savings account, or you have some vehicle or collectible that's worth a certain amount and it's going to grow so many percent each year. So in this case, I know it's growth because this is greater than 1. So then, in order to find out what the percent is, I write it as 1 plus R equals 1.29. Then I subtract 1 from both sides, and I get R equals 0.29, or 29%. Clearly, the growth one is easier to see. Now, sometimes, however, we have to determine how many times it's going to grow in a certain time period. All right? And that's the big deal with today. We finished up a little bit with that the other day, but we have to take a look at this. Okay, so it says pay special attention to how long it takes for the growth or the decay cycle. I just realized I misspelled cycle. Wow. to occur. So in many instances, the exponent or the x value is equal to the time divided by the cycle length. Okay, so that tells us how many times the growth will occur. So that sounds really abstract. So let's give you an example. I think this is pretty straightforward here. It says the number of bacteria in a tray doubles every 6 hours. How many bacteria would there be after 1 day? So there's a couple flags here. First of all, they change units on us. They're talking about hours here, they're talking about days here. So got to be careful with that. The other thing is, so 1 day is 24 hours. So I have to figure out how many of these cycles are going to occur in 24 hours. So 24 divided by 6, because that's how long the cycle length is, would tell me that there would be 4 cycles over the course of 1 day. So since they didn't tell me how many bacteria, and normally we would, I just have y equals a times 2, because it's doubling, to the 4th. Because there are 4 complete cycles. Now, let's actually look at our worksheet to determine what the next, to get some better idea of what's going on here. Let me adjust the camera a little bit. There we go. It says the amount of radioactive substance can be modeled by the equation y equals 180 times 0.78 to the x, where y is the number of grams of substance and x is the number of 4-year periods. Okay, 4-year periods. So that's the catch right there. So the initial amount of the substance is the amount that's in front. In this case, that's the 180. And it's 180 grams, because they say it's in grams. Now, what I want to know is what's happening. Is this growth or decay? And how much? Well, that's 0.78. That's less than 1. So that means it's decay. But then I want to know by how much. Okay? So 1 minus R equals 0.78. So subtract 1 from both sides. I get negative R equals negative 0.22. When I divide by negative 1, I get R is 0.22. So that is a 22% decrease. Well, they didn't ask for it, I could. And you need to be prepared for any of that. So, then we're going to know what X value will find the amount of substance left in the bloodstream after 20 years. Well, again, we have to go back here. So, 4-year periods, 20 years. So I have to figure out how many 4-year periods occur in 20 years. So 20 divided by 4 is 5. So that's what goes on this line. And I'm just circling it because I had all this other stuff there. So they want us to find the amount of the substance left after 20 years. Okay, so this is what I'm going to put into my calculator. And I happen to have mine here that I'm able to bring up for you. So I have 180 times 0.78 to the 5th. And so I would have 51.97 grams. I always round to 2 decimal places. So let's take a look at the next problem. It says the number of flies on a dead organism can be modeled by this equation, 25 times 2 to the x, where y is the number of flies and x is the number of 8-hour periods. So the initial number of flies, right here at the beginning, it's 25. So what's happening? This is doubling. I know it's doubling because there's a 2 right here. So what x value will find the number of flies after 3 days? Well, because it's every 8 hours, I know that there's 24 hours in one day, and so therefore there are 3 periods, 3 cycles in one day. Well, this is 3 days. So there's 3 per day, and we're talking about 3 days. That means that it's going to occur 3 times, or 9 times. So 9 cycles. So find the number of flies after 3 days. And let's see, to the 9th. So 25 times 2 to the 9th. That's not a small number of flies. That's 12,800 flies. Ew. Okay, number 3. Cameron bought a new car for $25,000. Okay, that's going to be my initial amount. The value of the car decreases by 10% each year. All right, so that means I have to start thinking about my equation here. Because what they're asking me is, how much will it be worth in 5 years and in 10 years? So, because it decreases, I know that it's going to be 1 minus R, okay, from that formula page. And that 10% is 0.10. So 0.90 is what's going to go in my parentheses. So 25,000 times 0.90, because 90% of the price is remaining. Then it's each year. So in this case, it's 5 years. And down here, it's 10 years. So I type this in, 25,000 times 0.90 to the 5th for the first one. So that car is now down to $14,762.25. But I need to find it again. 0.90, this time to the 10th. So after 10 years, it's down to $8,716.96. Not bad, actually, after 10 years. Okay. Number 4 says Elaine invested $12,000 in a bond that increases in value by 7.5% each year. Okay, so it increases, so that's 1 plus. And because it's 7.5%, remember, move your decimal point 2 places. So 0.075. That's what we're going to be multiplying by. So 12,000 times 1.075 to the third. Now, to save some time, I'm not going to type that into my calculator. I've already figured that out. You get $14,907.56. For 5 years, it starts the same way, but we end up with $17,227.55. Not a bad little money-making instrument if you have money that you could just let sit there. All right, so let's go to our next page. Let's actually talk about graphing and taking these and putting them on a graph. All right, so first things first, I have my table here. I need to find the points. So I'm just going to label them 0, 1, 2, 3, 4. You might as well do that for the next one as well. And what I'm going to do is I'm going to use a feature on the calculator that is really helpful in this situation. It's called the table feature. And you could do this on Desmos as well. I've showed you guys a few times. So second and graph gives me the numbers, and I don't have to do anything. So 0 and 64, 1 and 16, 2 and 4, 3 and 1, 4 and 0.25. All right, so let's plot these. Now I got 0, 1, 2, 3, 4. But I need to figure out what to put on my x-axis here. So again, I go to the next highest 10. In this case, that would be 70. 70 divided by 10 is 7, so that's what I'm going to count by. So 7, 14, 21, 28, 35, 42, 49, 56, 63, 70, 77. I don't have anything larger than that, so I'm going to stop. I'm going to plot these points now. So I have 0, 64, so about there. 1, 16, so about there. I'm just guesstimating. 2 and 4, that's about halfway. 3 and 1, that's real small. And 4 and 0.25, that's even lower. So I got this curve that's going to come down and get really close to this line. So here we go. Just do your best. The points are what matter the most. Now, because this is times 2, I could do this one in my head. So 0, 4, 1, 8, 2, 16, 3, 32, and 4, 64. Now, since 64 is the largest term, I'm going to, again, round that up to 70, divide by 7, and I'm going to use the same scale. And again, I'm not going to go any further than that because I don't need to. Let's see, 7, 14, 21, 28, 35, 42, 49, 56, 63. Yeah, okay. All right, so 0, 4, so about there. 1, 8, about there. 2, 16, about there. 332, it's about there, and 464. All right, so all right. So, in this question here, we have to be very careful. It says, your grandparents gave you 2 quarters when you were born. They promised to triple the number of quarters you have every year until you are 10. All right? So, I often find it easier to write the equation before I define my variables. So, I have 2 quarters, and they promise to triple the number. So, triple is times 3. And it's every year until we're 10. So y equals this. So I'm going to say x equals years. Y is the number of quarters. So how many quarters will I have by age 10? Well, 2 times 3 to the 10th. Okay. 2 times 3. Oops. To the 10th. That's going to be a lot of quarters, folks. Yeah. 118,098 quarters. That's a lot of quarters. So 0, 1, 2, 3, 4. And, by age 3. Okay, so we don't need the 4th one. So I know at age 0, I have 2 quarters. But since I'm tripling, after 1 year, now I'm at 6. Triple that, that's 18. And triple that, that's 54. And that's all there is to it. Okay. Your assignment is in Canvas. I will see you guys later. Have a great day.